So once again, a very good day. And now we're going to be looking at a few details because we've got just an hour since you've got approval for lecture-free week from midday. So in our last class, we're able to resolve the transmission coefficient for the quantum well. And we're also able to mention a few details about the tunneling of the wave function through the well. So I think right now we are going to consider the infinite potential well. I will try to run through as fast as we can. Okay. So for the infinite potential well, if you've been able to look through the tutorial questions, I think I tried to solve one of the problems for the quantum well laser using the infinite potential well model. So the idea is that we have a potential well such that it extends, say, to infinity, okay? This extends to infinity, such that at this point, V0 extends to infinity, and at this point, V0 extends to infinity. And here we have X. So for the purpose of symmetry, so if this becomes our origin, then for this dimension, which is the same as D, then this will be negative D over 2, while this will be positive D over 2, okay? Then at this point, now, if at this point V0 is the same as infinity, then at this point, at X equal to, at the origin, let's put it that way, then V0 will be the same as 0 at this point, since at this point, it is infinite. So here, we consider a particle confined in an infinite potential well. So this is a model for an infinite potential well, such that the potential function V0 is the same as infinity. Or if we put this differently, it means that region 1 and region 3, this being region, here we say region 1, region 2, then region 3. Okay, so recall that this extends to infinity as well. Okay, we call this E. Okay. Now, to describe this differently, what we are trying to say is that region 1, this region for which we have this boundary, and the region for which we have this boundary represents impenetrable wall. That is region 1 and 3 represents impenetrable walls. So this implies that the wave function at region 1 and 3 vanishes. So it means that the wave function is the same as 0, since it's impenetrable. Okay, now, if that is clear, then we can quickly put up a model, okay? We can quickly put up a model for this idea. Okay. So by way of extension, we already solved a few examples. Now, by implication, going from this analogy, so it means that the wave function at this boundary is the same as the wave function at this boundary is the same as 0. So if this is so, it means that the particles will be confined in region 2, since region 1 and 3 are impenetrable. So whenever V, which is the potential function, is infinite, the wave function must be 0 in order to satisfy the Schrodinger equation. And going by the last example we resolved, we know that the wave function is the same as the square psi, the x squared, which is the same as negative k squared psi. And we also know that the wave function k squared is the same as twice the mass than the difference between the energy functions divided by h cross squared. And we also know that the wave number k, more like the fundamental time period, if you recall your signals and systems, is the same as 2 pi over x naught. And if we try to draw the relationship, so let's assume we have a wave going this way, for which this could be time or x. So in your signals and systems, we made mention that this interval for which we have a complete circle is the same as the fundamental time period, T naught, for which the scale is time. Now that we have to consider the scale in terms of position, then it is the same as x naught, okay? Such that when we consider the time plane, then we have the angular frequency be the same as 2 pi over T naught, which is equivalent to the wave number being the same as 2 pi over x naught, okay? Now that we are considering this potential well, the infinite potential well, so it means that this boundary from this point to this point is infinite, okay? This is infinite. And then we have this dimension taking on values from 0 to d, okay? Now, if we try to, say, avoid symmetry, okay? We just want to avoid symmetry. Now, we can design this way to say, well, this is a model of where V is the same as infinity. Then we know this is the x-axis. Then the dimension of the confinement is the same as 0 to d, okay? And then we also know that the square psi, the x squared, is the same as negative 2m e minus v h cross squared psi, okay? And now, if we consider at this boundary for which v naught is 0, that is the square psi, the x squared, at v being the same as 0, then this is 0, so we have negative 2me over h cross squared psi. And also, when we consider at this boundary for which v, because at this point, v is equal to 0, then at this point, v is equal to infinity. So when we consider the wave function, the square psi, the x squared, at v being the same as infinity, then we have negative 2m e minus infinity divided by h cross squared psi. Okay? But outside the well, recall that the particles we have in this infinite potential well are confined. And then, if they are confined, it means that the walls are impenetrable because the particle will require so much energy, infinite energy, to be able to escape this wall. So since the walls are impenetrable, it means that the wave function outside the well is the same as 0, okay? Now, if the wave function outside the well is the same as 0, then this expression outside the well, then we are going to have the wave function being the same as 0. So if we replace this wave function to be the same as 0, then it means this expression is the same as 0. Okay? Now, since the wave function takes on values inside the well, inside this confinement, then it means that the squared psi, the x squared, is the same as negative k squared psi inside the well, such that the wave function therefore have a solution of this kind: a sine kx plus b cos kx. Okay? Now, we can actually verify if this is correct, okay? And for us to be able to verify that this is the solution to this second order differential equation, then we could substitute psi for this parameter. And once we do that, then we'll see if it actually satisfies the equation, okay? So in other words, we now have to compute the second order of this particular expression. So let us try that out. So let's wipe this and see if that is a solution before we move on. So it means that here, the psi, the x, will be the same as d. We're going to take the second order, the x, a sine kx plus b cos kx. Okay? So by chain rule, we're going to get the psi, the x will be the same as a k cos kx. Then if we differentiate cos, it's going to give us a negative sign minus b, then we have k sine kx. All right? So next, we want to resolve the squared psi, the x squared. So which is going to give us the differential of this, d, the x of ak cos kx minus bk sine kx, okay? So by chain rule also, we also know that if we differentiate cos, it's going to give us minus sign. So that's going to give us minus a, k times k will be k squared sine kx. Then we have minus. So if we differentiate sine, we're going to get cos. So this time is going to be b, k times k squared cos kx, okay? So this is what we have. And then, should we factor out k squared, then the squared psi, the x squared, is going to give us minus k squared into bracket a sine kx plus b cos that'll be b cos kx, right? And now you observe that this is the same as the wave function, and then we have the minus k squared. So hence, this is a solution to this expression. We just verified it, okay? Now that we have verified it, then we can go on with our solution, okay? So now if we get rid of this, we haven't verified that this is the solution to this, then coming back to this, we know that the wave function is 0 outside the potential well, okay? So it means that at the boundaries, at these boundaries, the wave function is the same as 0, okay? Then if that's what we have, so hence the solution of the wave function at the boundary is 0, such that this expression equates for 0. So we want to evaluate at x equal to 0, at x equal to 0, then at x equal to d, okay? So at x equal to 0, the wave function is 0, and at x equal to d, the wave function is also equal to 0. So if we resolve at this point, so we know that the wave function is the same as a sine kx plus b cos kx is the same as 0, okay? So for us to be able to achieve this expression, we have to put kx to be 0. So if kx reduces to 0, then the wave function here will be a sine 0 plus b cos 0. Now this should give us 0, okay? So we know that sine 0 is the same as 0, but cos 0 will give us 1. So it means that this is going to give us b times 1 is equal to 0. So b is the same as 0. Okay? Now, if we substitute b to be the same as 0 into this wave function, so we have a sine kx plus 0 times cos kx is equal to 0. So it means that psi is equal to a sine kx. Okay? Now, but at x equal to d, it now means that the wave function, which we already solved at x equal to 0, we now reduce to a sine kd. And this also is the same as 0. Okay? Now, since the wave function exists only inside the potential well, so it means that a cannot be equal to 0. So it means here a cannot be the same as 0. Since this wave function exists inside the well, it is only at this boundary it reduces to 0. So if a cannot be the same as 0, then sine kd must be equal to 0. Now, for this expression, for the wave function to be 0. So if sine kd has to be 0, then looking at our regular sinusoid, so at what point is this sinusoid 0? At this point, right? To infinity and to infinity, okay? So it means that if this is 0 at this point, let's assume this is 0, then at pi interval, we have another 0 when sine pi, then sine 2 pi is also 0, sine 3 pi is 0, sine 4 pi is 0, so minus pi, 0. So at this point, minus 2 pi all the way, okay? So at pi interval, then sine kd will be 0. So it means that k dot d must be equivalent to n pi, for which n takes on values from 1, 2, 3, all the way, where we have n is equal to 1, then we have pi, 2 pi, 3 pi, 4 pi, all the way. That is the only, now this is the only condition that will make sin kd to be the same as 0. Okay? So if that is clear, now if that is clear, so it means that k is the same as n pi over d. Okay? But coming to this expression, we have k squared, right? So this now gives us k squared will be the same as n squared, d squared, n squared pi squared rather, n squared pi squared over d squared. But recall that k squared is the same, or better still, k, from what you know, k is the same as the square root of 2me over h cross squared, such that k squared is the same as 2me over h cross squared. So it means that these two are equivalent, such that k squared being the same as this is the same as 2me over h cross squared. Okay, so this implies that the energy in the potential well is restricted to certain multiples of n, because in this case, you see that energy is now dependent on n, such that if we now cross multiply and make E the subject of formula, we now have E to be the same as n squared, pi squared, h cross squared over 2md squared. So since n takes on integer values, so it's an element of an integer set, let's put it that way, okay, such that n could take on values from 1 to 3, blah, blah, blah. So it means that the energy in the well is quantized. Okay? Now, if this is cleared, so it means that here you will now observe that at E equal to 0, at n equal to 0, there is no energy value. Okay? So from this expression, let's clear this, we have E sub n being the same as h cross squared. No, let's put it this way. N squared pi squared h cross squared over 2md for values of n taking on integer values. So you observe that the energy does not exist at n equal to 0. Okay? And you also note that the energy is directly proportional to the square of n. Okay? Such that when n is greater or equal to 2, the energy level doubles. So you can see when n is equal to 1, we have E1. When n is equal to 2, so then we now have, since this is proportional to 1, so this is now for E equal to 2, this is proportional to 2 squared, right? And n squared, that is 4. When n is equal to 3, E3 will be proportional to n, 2 to the power of 3, 9. So you see that at n greater than or equal to 2, the energy doubles. So it's not a symmetrical process, or more like a scaled process. It's not something like this. So it means that once we have the first energy level, the second energy level is twice this. And then the third energy level is more like 3 times, right? 1, 2, 3, all the way. Okay, so the energy level doubles in the well. Good. Now, if that is clear, so it means that at E naught, at n equal to 0, we have E naught. Then psi E naught of x is also equal to 0. So no state with quantum number n equal to 0 is satisfied since the wave function is 0. But now we still have a problem, okay? Because we now have that the wave function psi is the same as A sine KD. So what is A? So we need to resolve A, okay? Now, if you recall that, let's say, recall the probability density function, which is the modulo squared, the psi modulo squared or mod psi squared is given as this, which is the PDF. Then for us to be able to find a particle within the spatial range, we integrate the PDF mod psi squared dx, which is the same as 1. Okay? So what we now have to do is to take the integral of the mod squared of this expression. And this is going to give us the integral mod A sine, let's say kx. Let's leave it at x for now. Since we are differentiating, we are integrating with respect to x, kx dx. And we know this is going to be equal to 1 mod squared, right? So this is going to give us integral a squared sine squared kx dx is equal to 1. So we have the integral mod squared dx is equal to the integral a squared sine squared kx dx is equal to 1. Okay, you recall we resolved something like this in your signals and systems. So we just have to rewrite this. It's a trigonometric ratio. And you'll recall that, let's change the color. Sine squared kx plus cos squared kx is the same as 1. And cos 2kx is the same as cos squared kx minus sine squared kx. So if we now rearrange this, we know that this is 1, cos squared kx is 1 minus sine squared kx. So just put that 1 minus sine squared kx minus sine squared kx. So this is going to give us 1 minus 2 sine squared kx, right? And then recall that this is cos 2kx is the same as this. So it means that sine squared kx will be the same as 1 minus cos 2kx, then divided by 2, okay? So what we now have to integrate is this. So it's the same, it's equivalent to this. So now we have to integrate a squared into bracket 1 minus cos 2 kx over 2 dx, right? And once we do this, it's going to give us a squared into brackets. This will be 1 over 2, so that will be x over 2 minus sine 2kx over 4, okay? That'll be over 4k, right? Now, we know that this 0 to d, okay? Now, d is the same as n pi over k, because recall that k dot d is equal to n pi, okay? So d, If we substitute a 0 here, sine 0 is 0. Now, if we substitute a d here, so we are going to be having interval of n pi. So it means this expression also reduces to 0, so that we now have a squared d over 2 minus 0. So that's going to give us d over 2, which is the same as 1, right? So once we rearrange this, so this would be a squared d is the same as 2. So a squared will be the same as 2 over d. Then a will be the same as the square root of 2 over d. So hence, the wave function psi is the same as the square root of 2 over d sine kx. Okay? Beautiful. So now, we are meant to cover some other details, but before we do that, I would love to move right quick into the finite quantum well, okay? Because we are going to be resolving a few, some interesting problems too. You know, there are some of the problems I'm yet to upload on finite quantum wells. Okay, so we just have some few minutes. I'm supposed to talk about the density of states and the Dirac, the Fermi level. So, but I'll look at it still, but let's see if we'll be able to beat the official time we have today. So let us look at the finite quantum well. Now, we've been able to resolve the infinite quantum well. But now, what if the bounds is some finite value, okay? And if it's some finite value, then it means that, well, we should be able to scale through that potential barrier, you know, given a certain energy level. So, unlike the infinite well. So let us look at the finite quantum well. Okay, so you recall that for an infinite quantum well, the energy eigenvalues corresponding to the wave function was given as E sub n, which is quantized, h cross squared, or let's start with our n squared, pi squared, h cross squared over 2m d squared, okay? And for all potential values tending to infinity, and psi of x being the same as 0 outside the well, okay? So this is what we got for the infinite quantum well, okay? Now, for a finite potential well, V naught is less than infinity. So such that the wave function could propagate across the three potential barriers. So we are now going to have something like this, where we have region 1, region 2, region 3, and then we are going to have the wave function in region 1. We are going to have the wave function in region 2. Then we're also going to have the wave function in region 3. So the boundary conditions will therefore be given as we already know, okay? That the wave function in the first boundary is going to be the same as what we have in the second boundary, in the second region, be the same as what we have in the third region. So this makes the problem a little complicated. And the first time derivative of the wave function in the first region is the same as the first time derivative of the wave function in the second region, is the same as the first time derivative of the wave function in the third region. Okay? And to achieve the boundary condition, the solution of the Schrodinger equation will follow directly. Okay? Now, here we have to assume symmetry. Okay? So because of the complexity of the problem we now have to solve, we'll assume symmetry. Okay. Such that this entire dimension we already know is D for 0 to D, right? But this time, this is X, right? So if this is 0, the origin, then this will be negative D over 2, and this will be positive D over 2. Okay? And then we can now resolve this problem. Now, the reason the total length D is divided into positive 1/2 of the dimension and negative 1/2 of the dimension is because it gives us symmetric potential energy, okay? And this makes it easy to solve the Schrodinger equation. And once we evoke symmetry, then it means the solution throughout the x-plane can either be an odd or an even function. So that's the idea. So, so for ease of solution, so it means that the solution of the wave function over the x-plane will either give us even, which is cos, or an odd solution, okay, which is the same as sine. So the bottom line is we cannot have both, okay? So that's the idea, we can have both. And going by this, so it means that in the well, we are going to have something that looks like this. Which I showed, I think I made mention of this in our last class. So here we have symmetry. So we now have at the first energy level. So at the second energy level, we have something like this. Then at the third energy level, we have something like this. Then at the fourth energy level, we have something like this. All the way, okay? Now, for clarity, you see that here, across this boundary, this is a wave function, okay? Where this is 0 and this is D, okay? That's the full boundary, okay? But in our analysis, we now have negative D over 2, this is 0, positive D over 2, okay? So this is now equivalent to the energy band diagram. So if this is our first energy level, where n is equal to 1, so we have 1, 2, so this becomes n equal to 2. So we have 1, 2, 3, 4, then this becomes n equal to 3. Then we have about 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Then this becomes n equal to 4 all the way, right? And this is the same as the energy level. Okay, so this axis gives us E, okay, which we can say is the same as pi squared, h cross squared, because n has been taken care of, over 2md squared, okay? And then if we take the mod squared of the wave function, the PDF, for instance, then what we are going to get, so we are taking mod squared. So it means that at this point, we don't have negative, no negative. So recall we have our symmetry here, right? So this is going to give us our first energy level, which is all positive. Now, at the second energy level, we are going to have both the positive and the negative. Then at the third energy level, we are going to have the 3, 1, 2, 3. Then at the fourth energy level, we are going to have 1, 2, 3, 4. Okay. So this gives us a brief description of what we get, okay, in the well. Okay. So the next point is to address the fundamental problem we are meant to solve in this, in describing the entire process. Okay. And now, for us to do this, we have a few minutes, so let's just run through. You recall that we have the squared psi of x, dx squared is the same as 2m, negative 2m, e minus v over h cross squared psi of x. So this is second order differential equation. And you want to know that any state that has energy below the well edge is referred to as a bound state, okay? And these bound states are responsible for absorption and quantum confinement, and they'll become very relevant when we begin to talk about lasers, okay? So in the quantum well, the energy is larger than the potential, okay? So it means that E is greater than V. So that K, which is a wave number, is the same as 2m E minus V over h cross squared all squared. This will be positive, okay? So will be a positive value, okay? Okay, perfect. So now, I would love to pose a little question at this point, okay? Now, what would be the system of equations? Yes, let's put it that way. What would be the system of equations for the finite quantum well? I'd love you to unmute, please, and give me feedback. Are you still with me, please? Hello? the system of equations. Okay, let's do some name calling. Oluwatobi, can you hear me? Can you hear me, Oluwatobi? Okay, so can you tell us the system of equations we're going to have for the finite quantum well? Can you? Okay. Oluwatobi is not talking, so let's try to beat time. Okay, can you come again with the question? Okay, I just did. So, system of equations in what sense? Okay, relative to the boundaries. That's what I mean. Relative to the boundaries. Okay, let's come back then. Now, you recall that the Schrodinger equation is given as the squared psi of x, the x squared, being the same as negative k squared psi of x, okay? And based on symmetry, we already know that the solution will be the sum of sinusoids, okay? Okay, we have one hand raised. Oluwatobi, go ahead, please. You can go ahead. We can hear you, Oluwatobi. Can you go ahead, please? Okay, Oluwatobi is not talking. Okay. Okay, so let's move on then. Now, since we have been able to establish symmetry, the solution will be the sum of sinusoids, okay? That is, we are going to have sine and cosine functions. And outside the well, the coefficient 2me minus v over h cross squared is negative, okay? Outside the well. We've been able to establish that inside the well it is positive. So if that's true, then it means that k will be the same as j alpha, where j is the same as square root of -1, okay? So it means that alpha will be the same as 2m v minus e, because v is larger, e is negative, h cross squared, okay? Alpha squared rather, so that alpha will be the same as the square root of 2m v minus e over h cross squared for e less than v, okay? So you take note of that. And according to the symmetry theorem in quantum mechanics, if we have a symmetric potential, v of x, okay, the solutions are either even or odd and cannot be both, okay? So it means that we either have an even solution for which we have a cos function, or we have an odd solution for which we have a sine function. So, but it cannot be both, okay? The solution can't be both. So we have one. And then we already know that the wave function, based on the boundary conditions, that the wave function and the first time derivative of the wave function must be continuous across the boundary, okay? So that if it has to be continuous across the boundary, So it means that psi of x in the first boundary must be the same as psi of x in the second boundary and must be the same as psi of x in the third boundary. Please, I want you to take note of this particular information. It's going to help us a great deal. And the first time derivative in the first region is the same as the first time derivative in the second region is the same as the first time derivative in the third. If that is correct, so, and being that based on the symmetry theorem, okay, and based on the symmetry theorem, then we are going to have something like this. If, for instance, we already know that based on the symmetry theorem, we cannot have both even and odd components in the solution. It's either an even component or an odd component, okay? So it means that it's either even, that's the solution, having cos, or it's either odd, having sine function. So if, for instance, the solution in the well is cos, let's assume it is cos. Okay? So it means that we are going to have something like this in the well. So if we're going to have something like this in the well, okay, this is the well. This is the well. So we're having a cos function in the well. And we know that the wave function must be continuous, okay? So this is region 2. So this is region 1, and this is region 3. So it means that for this to be continuous, then this we have to go this way. And then this we also have to go this way, right? Then it means it's continuous. So if that is correct, then it means that at this point, we are going to be having a positive exponential, alpha x. And here we're going to be having a negative exponential, alpha x, for this to be correct. Now, what if it is a sine function? Let's assume it is a sine function. So let us assume the solution inside the well is a sine function. This is a sine function. So this is the boundary. So it means that inside the well, we have a sine function. So our solution is something like this. Our solution is something like this. It's a sine function. So it's odd. So it means that outside the boundary is going to come this way for it to be continuous. Okay, so this is region 2, this is region 1, this is region 3. So for the wave function to be continuous from between region 1, region 2, region 3, then this is what we get. So then it means that outside, or better say in region 1, we are going to have exponent negative alpha x, and here will be exponent positive alpha x for it to be continuous. And it goes on and on. Okay? So if we now have to resolve the problem in this case, like we have in our videos. So let us take, for instance, that we have to deal with an even solution. Okay, so let's clear this. So it means we have even solution. So it goes that way. So it means here we have b cos kx. So this is e plus alpha x, and this is c epsilon minus alpha x. Okay, so this is negative d over 2 then this is positive d over 2, okay? So since the system is symmetric, so we can say A and C are equivalent. And considering the boundary condition at x equal to minus d over 2, you recall that the boundary condition is the same, right? And also, the first time derivative in the first boundary and in the second boundary or the third boundary or whatsoever, they are the same, okay? Now, if that is clear, then for our first and second boundary, this and this, so it means that A epsilon plus alpha x is the same as B cos kx, okay? This is for x being the same as negative d over 2. And then we can now resolve when x is this. So when x is that, so we have A epsilon minus alpha, or better say, let's place it the way it is, plus alpha into bracket minus d over 2 is the same as B cos k dot minus d over 2, okay? And we know cos minus x is the same as cos x, right? So this means we have A epsilon minus alpha d over 2 is the same as B cos k d over 2. So we have our first equation, okay? And if we take the derivative, okay, the second boundary condition, if we evoke the second boundary condition, so we are going to have, in this case, alpha A epsilon minus alpha d over 2 is the same as k b sine kd over 2, okay? This is our second equation. And from these two expressions, if we combine these two, then we are going to get alpha A epsilon minus alpha d over 2 over A epsilon minus alpha d over 2 is the same as kb sine kd over 2 over b cos kd over 2. And this is going to give us alpha to be the same as k tan kd over 2. Okay, this is our third equation. Okay, and then from here, we know what k is and we know what alpha is. And once we are able to manipulate this, which we have in other videos, we now have k squared plus alpha squared is the same as 2m v naught over h cross squared, okay? And then, since we have this, we also have that alpha is the same as k tan kd over 2, then we can resolve these two systems of equation, okay? And once we do that, say we multiply this equation by d, then, and divide through by 2. So we are going to have something like alpha d over 2 is the same as kd over 2 tan kd over 2, okay? If y is the same as alpha d over 2 and x is the same as kd over 2, then this gives us something like y is equal to x tan x, okay? In a similar vein, we can play with this and multiply by d squared. So that will give us alpha d squared equal to kd squared, which is 2mv naught d squared over h cross squared. And if we divide through by 2, or say 2 squared, so this will be over 2 in bracket over 2. Then here we have 2 squared, right? And once we complete that manipulation, we now have, say, y is the same as alpha d over 2, x is kd over 2, then say r naught squared will be this expression, which is 2mv naught d squared over 4h cross squared. 2 squared is that. So this also will now give us another equation, y squared plus x squared plus r naught squared, right? Now, the system of equations in terms of y and x is of this form. And you see that this is the same as the equation of a circle, where r naught is the intercept, okay? So if we, for instance, now designate, going by what we have here, I think our time is almost up. Just spare me like 5 minutes, then you could go for your lecture-free period. Now, since we have y to be the same as x tan x, and y squared plus x squared is the same as r naught squared, and we already know that r naught squared is the same as 2m v naught d squared over 4h cross squared based on the manipulation we did. Now, if we also know x is the same as kd over 2, then k would be the same as 2x over d, okay? And we know the energy may also be expressed in this regard. We know k is the same as the square root of 2me over h cross squared. Then k squared is 2me over h cross squared. And then E is the same as k squared h cross squared over 2m, okay? So it means that E is the same as 2xk, this k, okay, 2x over d, all squared, h cross squared over 2m. And this is also the same as h cross squared over 2md squared times 2x squared, okay? Now, this 2x squared, we can write 2x squared in terms of pi, okay? So let's assume we write 2x squared, that's this, let's change the color. 2x squared in terms of pi, so that will be 2x over pi squared times pi squared. So once we take pi squared, so we still have 2x squared. So this now will be the same as x over pi over 2 all squared pi squared. And this, well, we can say this is in terms of the intervals of the x-axis, okay? So the energy term in terms of the x-axis can now be plotted. And once we plot this graph, this is what we are going to get. So we now see how we are able to use it to evaluate the energy level. So when we have 0 for even, okay, let's plot this. I'm literally done. Just spare me this little time. So the interval is now in pi over 2 interval. So at this other interval, we have pi. At this other interval, we have, that would be 3 pi over 2. Then at this interval, we have 2 pi. Then at this interval, we have 5 pi over 2. Then at this interval, we have 3 pi, right? So this is x, and this is the y-axis, x relative to y, right? Now, when we plot the even states, right? So we are going to get this. Let us change the color for the even state. So it's going to come something like this from the origin, because it's a tan function, right? Good. And then The next interval will be at pi. Then we have 2 pi. All the way, okay? And then when we now plot the equation of the circle, we'll see that it crosses this way. Right? That's the circle all the way. So this point of intersection gives us the energy level. Okay, that's where I'm going now. And when we also try to resolve for, now recall that this is the even component, we just even, okay, when the solution is even, okay? Now, when the solution is equally odd, then we can also plot the same. Once we run the analysis, then you can look up the video for that. So I just have to run through, and then the solution gives us a curve, a tan function also at this level, then a tan function at this level, then a tan function at this level. So this is the odd solution. So what's the implication of this graph? Okay, so here we have that n, this is n equal to 1. Here is n equal to 2. Here is n equal to 3. This is n equal to 4. Here is n equal to 5. At this point is n equal to 6. All the way, okay? So with this, we have a plot of y equal to x tan x, then y is equal to x, negative x cot x. Then we have the equation of circle x squared plus y squared is equal to r naught squared. Okay? Now, you will observe that at this point, this is E1. At this point, we have E2 at this point of intersection. So we are able to tell the energy level. So no matter how small R naught is, we must have an energy level. No matter how small the circle is, because this goes through the origin, okay? So no matter how small it is, there must be an energy level. So as R tends to 0, we only have one energy or one solution to the Schrodinger equation, as we only have one state. Okay, so this will bring us to density of states, which I'll love you to review and all of that. Hence, we are able to determine the energy in the well, say E1, E2, all the way. So here we can now see that the energy is actually quantized. H squared pi squared over 2md squared. Okay? So I think this is a good place to stop. If you have any question, I'll entertain that, and then we could call it a day so you could have your lecture-free moment. Any question, please? Is the course rep in class, or are the course reps in class for both programs?
Yes, sir.
Okay, so any question at the moment before we call it a day?
Well, it's clear for now, sir.
Okay, so do have a great day. Bye for now.